I'm not using any text there. No, not using. Okay, let's start today's talk. So it's a great pleasure to have Apoorva today present this Nobel Prize and Breakthrough Prize in Fundamental Physics talk. So this talk stems from the Nobel Prize in 2023, which was given on entangled states from fluid technology. So I'll just read the brief. So this was given to Clauser, Aspect, and Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So obviously, Apoorva is one of the key players in this framework. So it's a great pleasure to have him. Apoorva is also the chair for our IQTI IISc Quantum Technologies Initiative. And on a personal remark, we have Optimus in this IQTI initiative and also Apoorva, who's a realist. And he always injects a dose of reality in whatever we are doing in the center. So it's very nice to have Apoorva with us. So Apoorva is a professor at CHEP and convener of IQTI and IISc Quantum Technology Initiative. He obtained his MSc in physics from IIT Bombay and his PhD in physics from Caltech. He has extensively worked on lattice gauge theory investigations of quantum chromodynamics. He's also notable for his work on quantum algorithms and the application of information theory concepts to understand the structure of genetic language. He has been exposed to the subject of quantum computation since his graduate student days at Caltech, and he has been the subject at IISc for more than 25 years. So, without further ado, Apoorva.
Okay, this is going to be a tale of two prizes. So it so happens that Nobel Prize and the Breakthrough Prize in Physics this year ended up in the same subject. And that is actually a great advertisement for what is considered important and what is going to happen in future. And I am quite familiar with this topic. As a matter of fact, I have been teaching it at IISc for more than 25 years. So many of you probably haven't been around that long, but there are a few who are familiar with this. So let me acknowledge the credits first, but a lot of material I have taken from the websites of the prizes themselves. And if you want details, there will be a lot more available there. And there is a mistake here. I'm supposed to give a similar talk on Nobel Prize in the biology department on Friday, which is the day. I'll put it here, and if you spot any other mistakes, so just catch me. So let me start with the basic introductions. These are the three Nobel laureates in physics this year: John Clauser, Alan Aspect, and Anton Zeilinger. The citation says that for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. What explicitly they have individually So Clauser's contribution is develop base ideas leading to a practical experiment. Aspect's contribution is develop the setup using the communication loophole. And Zeilinger's contribution is started to use untangled states with refined tools in a series of experiments, in particular demonstrated quantum teleportation. So all these topics are basically technological progress, which confirms quantum theory predictions and puts it on a firm ground. What about the other prize? It has been given for foundational work in the field of quantum information. And it is shared by Charles Bennett, Jay Brassard, David Deutsch, and Peter Shore. What are their contributions? Well, Bennett and Brassard initiated quantum cryptography by devising the practical way to send secret messages with the users who share no secret information initially, and showed that entanglement a useful, quantifiable resource by devising quantum teleportation. Deutsch defined the quantum version of a Turing machine, showed that it is equivalent to a network of few quantum logic gates, and designed the first quantum algorithm that surpasses the best equivalent classical algorithm. What showed is he invented the first quantum algorithm that is clearly useful. Designed techniques for quantum error correction, and his ideas paved the way not only for today's fast developing quantum computers, they are at the frontiers in the study of metrology and quantum gravity. So these topics are basically using quantum theory features leading to technological progress. So it goes either way. As I highlighted in the previous slide, there is a technological progress confirming theory, and there is a theoretical work leading to technological progress. So the Nobel Prize is given to experimental work, and breakthrough prize is given to theoretical work. As it happens, Nobel Prize is more prestigious, but breakthrough prize has more money. So the experimentalists actually need more money. Theorists don't need that much of. So you can take science now. But money breakthrough prize is $3 million divided between 4 people. Nobel Prize is about $1 million. So the story started long back. Those many important questions are no longer allowed. And one of the prominent characters was, of course, Albert Einstein. He posed this question, famous so-called EPR paper. It has a title, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Remember the words. It's talking about quantum mechanics being complete. Not
$1 million.
whose talk, of course, lots of this kind of statements, and you have to be aware about what Einstein actually wanted to do. And the version which we remember from this EPR question is actually proposed by David Bohm, and he converted problem which was in an infinite dimensional space in the EPR's original paper to a finite dimensional space. where you don't have to worry about limits and convergence and all things like that, and experiments can be performed much more cleanly. After this paper, Niels Bohr replied in the same journal with the same title. But nobody remembers that paper because Bohr was just repeating his Copenhagen interpretation and that's all in the past. What people remember is the reply from particularly for the two words which have gotten stuck in our description of the problem. One of them is entanglement, and that is discussed in this paper of probability relation between separated systems. And another is our famous cat, whether it is dead or alive. And
Question. Schrödinger's paper where he mentioned entanglement was written after Schrödinger read the EPR paper.
yes, this is in reply to Einstein's paper, both of them. It's very clearly stated in the papers themselves. And that elaborated what Einstein put forward in a language much more suitable for quantum mechanics, and that's why these questions have been around for a long time. And this was sitting for many years in various journals as well as lots of conferences, etc., until John Bell came along. This paper, in some sense, came out of the blue. There is no detailed discussion about various things which happened before, but directly attacking the problem and providing a clean solution. And this, there's a gap of about from here to here about 20 years. And after that, there will be much more work, and many of these articles are available in this nice book called Speakable and Unspeakable in Quantum Mechanics. Let me now go to the question. More probably a puzzle. And this involves these two words, originally from Greek, and people don't understand it in colloquial language, I'll just point out what they mean. One of them is ontology. It basically asks, what is reality? What exists, irrespective of observers? Whether somebody is looking at things or not looking, it doesn't matter. And the other word is epistemology, concerns what is observed. And naturally, it brings into play the point that who is an observer. And then can put all kind of labels on it, whether the observer is only an instrument, if there's a conscious person behind it, etc. And the debate of these two words is still not over. It still goes on. And the question is how much we can narrow it down. So here are some facts. That quantum dynamics produces probabilistic outcomes. Why and how? And what role does the observer play in quantum measurements? These are the important questions. And then what people tried for a long time is to answer this question, which is narrower than whatever I have written in the first line. Can the quantum indeterminacy be explained as arising from so far unobserved hidden variables, as in the case of statistical physics. This kind of a description is not uncommon. In physics, generically, we have theories which are called effective theories. These are valid within specific ranges of parameters, and there can be a lot of stuff outside those ranges, which well, we can ignore while dealing with the effective theory in a certain sense. And the common example which people learn in statistical physics is the Brownian motion of a particle in a fluid. It happens because the fluid has some underlying structure, essentially atomic composition. And what you see here is the consequence of this atomic composition, whether you know about atoms or not, it doesn't matter. It can be included in an effective theory. So this paradigm is very useful. And what does the effective theory then do? That variables which are outside, you can call them the hidden variables, they must have a distribution if you want to get probabilistic outcome, various possibilities. But even when these variables outside the effective theory are integrated out, something is left behind. And what is left behind includes observable parameters and contribution to correlations. Those are components of the effective theory. For example, of Brownian motion, what you get an observable parameter is temperature. Temperature is a consequence of atomic structure. The atoms are moving around, they have certain kinetic energy, and the temperature is measure of their kinetic energy. And there are contributions to correlations as well. You put it as some other effective description. So that is what can happen in quantum mechanics as well. You see peculiar things, and maybe something is integrated out, and it is leaving behind this kind of effects. Can you understand quantum mechanics in that particular way? And that is the limited questions of having some sort of unobserved hidden variables underlying whatever is present in quantum mechanics. You have to keep in mind that there is another very well-known theory of relativity. It is local. But irrespective of this locality, you can have these physical parameters and correlations which arise from global conservation laws. And they have no conflict. Let me give an example at this stage. At this place, a little bit in the past, we had the festival of the law. People burst crackers. Now think of a situation, a cracker burst, one half went in one direction here, and some person saw that. He can immediately infer that the other half is on the opposite side, and it can be predicted without having to go and check it. Why? Because we know that there is a conservation law of momentum, and that is the global relation. It allows me to instantly predict something far away. The sum of everything has to be zero, and that is going on. Lots of this kind of global conservation laws, whether it's momentum, energy, regular momentum, charge, so on and so forth. They are global constraints, and they have no conflict with locality of limits. Must keep that in mind. But there can be other kind of correlations which exist in quantum field, both in space and time. And that is the point of this whole fundamental discussion. What is the origin of such peculiar quantum correlations? So here is an explicit example. This was considered by Bell, and I'm going to write some equations. So follow the derivation very closely. It will get over in a few lines. Consider a two-particle singlet state. Singlet state means that the angular momentum is created at a common origin, and then worry about how it will evolve when the two components separate at a space-like distance. This is the standard quantum notation. It allows a state, which is a superposition of up-down minus down-up. That is the singlet state. How is the singlet state produced? It has to be produced by a conservation law. No way out of it. So there was some event in the past which produced this correlated pair, and then they went their separate ways, and now they are distance and they cannot instantly communicate. There are lots of examples of the singlet state that one can find in actual world. The simplest situation is consider a cascade decay of atom where it goes from zero angular momentum to another state of zero angular momentum while emitting two photons. And conservation tells you that some of the angular momentum has to be zero. There's another possibility which is common in particle physics that you have a spin zero particle which then decays into two photons, like R0. And conservation laws tell you that it will produce this kind of zero. No conflict with that at all, either with quantum mechanics or with me.
I think it's absolutely essential to state here that the two measurements, A and B, are not done on the same system, but on identical replica of the same system. In one replica, you measure A, in the other, you measure B. And it's not that you measure A and then you measure B as a consequence of the same realization.
Yeah, but you can measure on the same copy also if you want.
But then A and B are non-commuting. It's okay.
Yeah, all those things will come. So what is done is one component is measured along direction A, and another component is measured on direction. The two operators which are measured are on different objects. That is why they communicate. They are also at a space-like separation, so that the result of the measurement cannot be instantly communicated with you. And we know what the measurement outcomes are going to be for this a simple setting that whatever A measures, whatever B measures, the values are either plus or minus. So there is no other choice. It's a finite dimensional space. So now trying to describe this situation using this hidden variable description, where you have some common hidden variables, lambda. They have the weights rho of lambda, and then you can write the correlation between these two measurements as a weighted average over what is measured by A and what is measured by B. The assumption is that this lambda came from a common origin of the two objects, so it is the same for both the particles, whatever it may be, we don't know, and what are the weights, we don't know, but we impose the normalization constraint, which is quite straightforward. Now, the first thing which one can notice is the conservation law implies that the value of B is the same for the negative of the value of A, then the two measurement directions are the same. That is one part. But what we are interested in is the situation where E and P are neither parallel, not orthogonal. These two situations are the one where the conservation law will solve your problem and you do not have something extra to say. To take this direction to be not the same, define this particular correlation. Now consider the results between one pair where A and B correlation is observed, another pair where A and C correlation is observed, and then you can write it as a simple difference of one minus the other, but by a little bit of trickery, it is factor out one of these terms, and the other can be written as a complement. It is a consequence of the fact that the answer is plus or minus 1. So here A of B is appearing twice, but square of it is equal to 1. So it is equal to P of A and this of, sorry, amplitude at A and amplitude at C, and that is equal to the subroutine. Next step. Use the triangle inequality. It says the sum of two terms taken in absolute value is less than the sum of the absolute value of the two terms. Very true in one dimension, but it's true in general vector spaces. So I take the modulus of both sides. The summation is the equivalent of the integral. There are various objects. I will put the integral and the sum at the same footing. There is a negative sign here, which I'm just shifting on the other side of the equation to write it in different order. It is a modulus. And then I get a modulus sign on the right hand side of all these individual factors. And then you can simplify. What is the modulus of this amplitude value? Well, the amplitude values are only plus or minus 1, so this is equal to 1. You can just drop it. What is the last factor? 1 minus product of two amplitudes. Amplitudes are plus or minus 1, so this last factor can either be 0 or it can be 2. And so the modulus sign can also be dropped there. It's always positive. And then there is this weight in front. It also has a modulus sign. And assume in analogy with statistical physics that the weight is positive. In that case, you can drop that particular modulus sign also. And so now all the modulus signs on right hand side are gone. What do you have? You have d lambda, rho lambda, and so on, which is equal to 1, the normalization integral, and d lambda, rho lambda times this last term, a, b, and ac, which is by definition the value of this correlation between b and c. And this is Bell's inequality. This difference is smaller than this particular value. This quantum theory violates. You can ask what this corresponding observation will amount to in the quantum language, where it is a polymetrics dotted with A and polymetrics dotted with B. Expectation value, you can evaluate by explicitly using these scales, but it's much more easily seen that, well, I can write this dot product out and then it will be sigma x times ax and sigma x times bx. Once you have both the polymetrics is the same, I can use the conservation law and then it will reduce to ax, bx, ay, by, it just gives a dot product. And that means this value, which I was writing here as a correlation between these two terms, is minus A dot B. And now one can think of lots of configurations which do not respect this inequality. For example, A can be up, B can be pointing at 45 degrees, and C can be horizontal. And then the left-hand side will be A dot C, which happens to be 0, A dot B, which happens to be 1 by root 2, and the right-hand side is 1, and this one is a minus 1 by root 2. 1 by root 2 is about 0.7, so this is about 0.7, and this is about 0.3. It doesn't work. So the question is why? What is buried inside here, which you must modify to understand quantum theory better. So this is what these experimentalists now measure by choosing specific direction of A, B, and C. Various levels of sophistication. The first work was done by Clauser. Clauser actually also produced a simplified version, which is easier than the choices of directions, which was done in Bell's paper. It is known just by its acronyms, CHSH version. But these pictures are a better explanation. So the correlation which was measured is one spin pointing up and the other spin pointing at 45 degrees. Important that these are not parallel. And then you obtain certain values, and the values again is what quantum theory aspect made this much more sophisticated. Because when Clauser did his experiment, he was only a postdoc. Didn't have any funds. So this experiment, the first experiment, was done by picking out laboratory equipment which other people had discarded, and he assembled that in some basement lab and carried out this experiment. It's a great story. And when it confirmed what I was doing in quantum mechanics, there were lots of loopholes. We didn't have the what you call equipment or the access to remove all kind of questions that people would pose. So one of the loophole was communication, which is between two measuring instruments. Was it possible? An aspect actually removed that loophole in this more elaborate setting and more sophisticated equipment. Again, a pair was produced. The two directions which are observed. This is the CHSH version of the inequality. Here are the two directions which were used in the detector are virtually orthogonal. This is what this picture are trying to denote. And the other side, these two directions are again mutually orthogonal, but at 45 degrees compared to this one. Having mutually orthogonal directions get an advantage that nothing is lost. Because when you measure, it's either landing up here or landing up over there. And that helps in removing certain kind of doubts. And to remove the communication loophole, he made this measuring instrument flexible, that it can be chosen as a polarizer which rotates. And then you choose the setting of this polarizer kind of instantaneously so that the measurement here does not have enough time to communicate the measurement over there. You have to flip those polarizers much faster than the traversal time of light between these two settings. And that removed this loophole, which is a communication. Can these two measuring settings communicate with each other? They can't. Then the experiment was carried out and the whole thing was confronted. Then came the work of Zeilinger, which refined it further. That here you are choosing the settings and say that they are random, but where are the random numbers coming from? Maybe they are coming from all the past history, and even if you believe that they are independent, they are not really independent. So we added a further twist that the random numbers which selected this measurement settings actually came from light coming from some distant galaxy. You detect the signal, you can get some flicker noise from there, etc. And so they have no correlation in the random numbers coming from it, and that kind of loophole was also removed. The other part was the same, and Zeilinger then went on to add many more things with this kind of settings. But that is the setup which removed all this uncertainty about communication loopholes and how you randomly select the basis, etc. Quantum theory still came out. So that is the story. And now the question, how do you get out of this problem? And the simplest answer is that at least one of the assumptions in Bell's derivation has to be given up. Question is what and how. One does not want to give up conservation laws or causality. So that will be too much trouble in lots of other areas of physics. You don't want to go there. So the most common way out is through a locality. So the hidden variables, whatever they are non-local. So then you want to save yourself from spatial relativity and say that, okay, these are non-local, but they're not observable, so you don't care. And so spatial relativity will not land up into trouble. And then a fifth example of this is the de Broglie-Bohm theory, which is actually older than Bell's theory. It was around, but it was just explicitly pointed out that it is one of the solutions which discards locality using unobservable, non-local hidden variables, and then it is equivalent to quantum prediction, which is fine. Another way out is something which is called statistical independence. We say that hidden variables in some way depend on the measurement settings, whether you like it or not. When you decide on a particular setting, it will choose what hidden variable you are measuring. And people have constructed all kinds of variations on it. These are some of the names: super deterministic theory, retrocausal theory, super measured theories, etc., etc. And why such a thing is allowed? Because you have to keep in mind that having a correlation is not the same as causation. Do not confuse these two particular words. And here they use correlation, but do not say anything about causation. There is a correlation between the measurement setting and what you measure.
Sorry, what's retrocausal mean what?
Going back in past.
Like future affecting the past.
So anyway, these are theories again which have been explicitly constructed and they get around to it. But you can ask now, what is in real quantum mechanics that we use to do all the calculation? It has neither of these. And it can feel of something else. And that is positivity. The way which I wrote down as rho of lambda, they can be negative. As a matter of fact, the same symbol is used for the density matrix, which is exactly the weight of various positives. It is a Hermitian generalization of the classical probability distribution. So you don't have only numbers between 0 and 1, you have complex numbers. And once you put that in here, this is the step which gets modified. Let rho lambda be the density matrix, and then the whole equation has no trouble at all. It will produce all the consequences of quantum mechanics. And there is a certain cleverness which you can introduce, that you can choose a basis in which the density matrix becomes linear. And this basis gives a density matrix in a form which was written down by Wigner, called the Wigner function. It is a smeared weight distribution in the phase space. And it's again historically important to remember that Wigner function was written down by Wigner even before the PR paper. So these are all standard quantum mechanical description, but the difference is that this Wigner function, whatever it may be, it's not observable in the same sense as the various quantities for which we take expectation values. It will involve simultaneous coordinates like in space. We can have, for example, both coordinate and momenta. And what it will measure is an average value over a certain smeared region, not a value of a point. And the smeared region has a sign of Planck's constant. This is something which is also automatically used in counting states when you are doing quantum statistics. And this is where the quantum mechanics answers the question that yes, you can have a Wigner function which plays the role of reality, but it's weird. It is not a probability distribution, it goes a little bit beyond. But you cannot observe it completely. You observe only some part, which is the role of epistemology. And what is the some part is the smeared value over a certain area, and then everything is fine and good. This is how the quantum mechanics answers the question. And one can now the question back in another words, what is it that produces this Wigner function?
So the weights being negative doesn't have anything to do with the nature of the hidden variables that's unfetched, right? Is that true?
Yeah. You can ask a question, where did the Wigner function come from? That is at a different level. But let me tell you a little story at this point. That we deal with partial differential equation and solving them as mathematical physics course. Take the diffusion equation. There's a rod and there's some temperature, and then diffusion equation ratio how the temperature gets smeared out. It's a function of that. So how do you solve this equation? The simple method is to write the temperature in a Fourier series expansion, and then the differential equation becomes a Once equation. You solve the value of the Fourier coefficient, and you get an answer that the whole temperature is given in a series of some values find the Fourier eigenvalues. So that smart student can ask. These Fourier eigenmodes are sines and cosines, and they go up and down. They have positive values and negative values. How are you writing a temperature which is completely positive in terms of these eigenmodes which have mixed up signs? You can think about whether this question occurred to you or not at all. And the student is smart, so he asks the questions to the teacher, and teacher is not so smart. So what is the response? This is a phrase very famous by Bombay. What are you doing? The physical reality should not be demanded of mathematical method. Fourier questions are fine. They can be on the eigenfunctions and eigenmodes of the system. When you are using them, calculate the temperature. Why are you demanding that each individual term in the Fourier expansion has to be positive? So, just an illustration that these questions are not common only in quantum mechanics. You can have them crop up in other settings also. And that is why this having negative rates is a different kind of status. You can ask where it came from, which will be a different question. And there is a further question which I haven't paid any attention to. The dynamics of what happens during the measurement is still an open problem. You will give a path to indicate where it is going, but it is still an open problem. So that ends the story of the Nobel Prize. And then we just do this, shut up and calculate. And that is the story of the breakthrough prize. We have the full mathematical formalism. We can calculate various things, see where it goes, and make those things available for technology. So the first thing in that list is the so-called B384 protocol. The first two B's are for Bennett and Brassard. And it has an IISc connection. It was proposed for the first time in the 75th anniversary of IISc's founding in 1984. Here, not in this room, but in IISc. And well, it was a nice paper, all completely correct. It went into the proceedings also, and that is a standard reference. But as it happens, it's went into proceedings for many years until the subject was fashionable, and now it is all over the place. And actually, it is so simple that I believe that it should be made available in undergraduate level. Doesn't require fancy equipment either. And actually, since this was proposed at IISc, I hope that IISc will do that job of putting it in undergraduate level. What does it do? It uses the fact that superposition allows non-orthogonal states that cannot be discriminated with certainty. So if you develop what is called a key distribution system using non-orthogonal states, it can become a communication method. Then it cannot be surreptitiously intercepted by an eavesdropper. Eavesdropper can be given arbitrary, unlimited computing power without introducing a disturbance that is detectable by the two parties. And why this disturbance occurs? Because the states are non-orthogonal. Measure then the projection. And both the states can have components which can give projection. And if that happens, these are communicating parties. We detect the disturbance and say that, okay, somebody is messing up with our communication. That's it. That's the another protocol has this fancy name, teleportation. And it actually uses entangled states. It's important to keep in mind that the entangled states have no communication capacity of their own. If you measure it, you will get +1 and -1 with equal probability, like a coin toss. Completely random. But such states can still be used to convey quantum state information to a distant location. And being quantum mechanics, what it is, when the information is transferred from one location to another, it is zero from the original location. You can't have a copy. So this can be done with finite amount of classical communication and without any material transfer of objects. That is a teleportation protocol. The information disappears from here and appears here. Doesn't matter how complicated the information is, the quantum numbers can describe generic states with complex numbers, but the classical communication protocol will be just a few bits. There is no way of describing a real number with a finite number of bits, but that is not a hurdle here. So this was a protocol again written down by Bennett and Gasser, and of course now demonstrated in enough number of labs. Then the contribution by Dodge. How to make a quantum computer. So what he defined quantum computer to be is any device that can simulate any physical system, arbitrary accuracy with finite means. Finite means is important because physical system which you are trying to simulate is also finite. Nothing is infinite in practical scenarios. So there can be a universal quantum computer which does this job. And then he showed that this quantum computer is equivalent to a network of only 1 and 2 qubit logic gates. Well, actually, Deutsch had 3, but now people have gotten around to having the 3 qubit gate, 1 and 2 are not. So that is again something quite simple, similar to what is there in Boolean logic. And then he proposed another tool, an explicit algorithm using such a device that you have a problem where the function is either constant or balanced. Constant is all the values are equal, and balanced means half of the values are one type and the other half are of the other type. And with superposition of states, Deutsch showed that this can be distinguished by just one function call, whether the function is constant or balanced. And one can try hard to figure out what is the best classical computer that can do. Well, it will require several function calls. At least 2, because you have to distinguish the possibility of constant or balance. If we make only one evaluation, you don't know what is the other one going to be. So this was an explicit example that something better is available. And then the time came for making useful quantum algorithm. And the first step was to show. It showed that quantum Fourier transform solves the period finding problem exponentially faster than what is possible for any classical algorithm. Fourier transform is something very common in quantum theory anyway, and he just used it in a clever manner to demonstrate this solution. And one application of this period finding problem turns out to be factoring large numbers. And that becomes the result that you can factor large numbers with polynomial effort, polynomial in the number of digits of the numbers, while the best known classical algorithm requires super polynomial effort. And this factoring of large numbers is an important problem because the RSA public key crypto system heavily uses it. So if this algorithm becomes applicable on a quantum device, we have to find a different crypto system. That is the status. Or did something more also, and that is to construct a theory of quantum error correction. It had various hurdles that the states are continuous, not discrete like in Boolean algebra. There is a restriction that quantum states cannot be copied. So a simple repetition kind of code, which we use all the time, cannot be used. And there are irreversible projective measurements which can disturb the system if you are not careful and spoil the signal. And Shore answered all these questions by a clever design that you can correct errors even when the states are continuous. You do not copy anything, and you do not disturb the signal, but you get rid of that. So that is a clever separation. And what it showed is fault-tolerant quantum computation is possible once the error rate is less than some threshold. What that threshold value is dependent on the hardware and the implementation. So it's a number you have to work out with a lot of details of design, but it's a finite number, it is non-zero. So if you are able to take error rate below this threshold, the quantum computer will run, protecting the signal from any error that may come along and producing a result which you can consider to be a reliable outcome. So this is a little bit of a technical formalism, but it's a breakthrough. It says that such things are possible. And it turns out the ideas which are buried inside here are also useful in other settings, which are also practically important. One is performing high precision measurements. And this procedure in various cases allows you to go below the threshold of central limit here. The error does not have to decay as 1 over square root of n when you measure the result n times. It can be made to decay faster. And it is also useful in understanding correlations which are present in the quantum many-body systems as well as in quantum gravity. In particular, the methods which are based on so-called tensor network states quite closely mimic the error correction codes. So they are being put to use in different topics as well. So this is the contribution in the breakthrough prize, and one can ask, where are we going? And these are some of the ideas which are being developed. You can make hybrid devices having both classical and quantum systems. You can make special purpose quantum processors. You can do modeling and simulation of various physical systems. you can do efficient data analysis of quantum experimental results, and so on and so forth. So that is a exciting part of the future, and I will kind of advertise a little bit about where we are going, partly because this is also our effort in the IQTI group about what all things are interesting to do, the features which we assume in quantum technology are described by these words: superposition, entanglement, fringing, tunneling, are all part of the quantum theory. We just have to figure out how to put them together to do something useful. And here is a kind of list of how it is happening and how soon. There is a this traffic light signal. People are also already doing good things in sensing and metrology, combining these ideas. Development in communication and simulations are already ready to go. Okay. This stuff is a little bit farther in the future, but there is a payback which will happen to the feedback or to foundations of quantum theory. And the most important part of this is a understanding of what happens during vision. The technology will provide you different tools to explore that particular question. And finally, of course, we will make a quantum computer. Of course, there is one big technological problem that quantum dynamics we know to be highly fragile. And so it is not going to work in generic arbitrary situations because the signal will get destroyed. So we have to work in protected settings in a nicely cooperative structure. But that is what we are trying to do, and don't come on to saying that quantum computer is going to do everything. Probably not going to work that way. They will be all kind of special purpose devices. And there's a competition. The classical technologies are also pushing various things in new directions. And this word, quantum supremacy, has to be accepted with a pinch of salt. It's a moving target. Things will happen in both directions, and you don't ask what is the winner, you take best of the both worlds. That is the viewpoint. And a little fact for the technological or the hardware side is the number of physical qubits in a quantum device is approximately doubling every year. This rate is faster than the well-known phrasing of semiconductor industry, goes under the names of Moore's law, where things have been doubling every 2 years. This is doing a much better job. We don't yet know how fast we will have something which will be useful in practice, but it is an exciting area to work with. Thank you.
It's a little comment about hidden variables. So, as a student in Tel Aviv University, I had the privilege of hearing a lot from Yakir Aharon about this. Yakir Aharon, at someone who was very close to David Bohm. David Bohm was the main figure who tried to pursue this paradigm of hidden variables. As far as I understood and understand today, the main idea was that there was a conceptual gap in quantum mechanics, which was non-locality. But it's very hard to conceive even what non-locality is, and Einstein had the difficult. But when it comes to a point that we need to make the theory of hidden variables more and more complicated and intriguing, and eventually claim that those hidden variables themselves are non-local, you gain nothing, so just abandon it.
This last time. This lead, when they
These are inputs which are protected in a limited sense, not in the sense of fault tolerant computation, but they are still protected good enough so that you can get a good signal out.
So, but you are asking what platform? Superconducting qubits is the
This is happening everywhere. Only thing the starting point is little different in all of them, but they're all done.
I think just to add to this last statement, rather than thinking of just the physical qubits, IBM has also defined this thing called quantum volume. That's another interesting way to think about, where you also think about like the gates.
What is the quantum volume?
So you also make Apoorva. It's a step to present.
Quantum volume is number of qubits multiplied by how many time steps you can work with. The signal is a kind of
Before it,
probably it is that they have a more sophisticated ways of describing it, but it's basically a product of space and time. Number of qubits in the space, how many clock cycles you can run is
More questions? Yeah. Very regarding this here protocol B8 and it's teleportation, right? So one is but both kind of get possessed. One is for non-orthogonal state, and the deletions are only the orthogonals, or might be something.
no, you measure it in the different main basis.
Yes, sir. No,
They are mutually orthogonal if they are correlated. Then two qubits.
but it depends on the projection. Again, if you measure something, then instantaneously the information goes to the other.
No, it's not that. Measure something in the main basis here. You get discrete outcomes, but it's an orthogonal basis. So the simplest protocol of only one qubit transmission, you get one of the four possible answers, which will split those four answers to the other side, which is equal to sending two qubits, sorry, two bits, two classical bits. And by performing certain operations based on those four values, you can reconstruct the split of the others. So it has to follow causality. That is not a doubtful set.
Very happy that you mentioned part of this breakthrough happened here, right here at IISc. You also mentioned set up for a cell-guided program. What exactly is the hardware and how do you set it up?
Hardware is not that particular expensive if you want to implement it as a product. That will tell you that it already exists in various labs of the campus. I'm just saying that it can be simplified. You don't want to measure things at high pitches and etc. But just as a demonstration, that can be put in an internet.
Just a quick question regarding the Bell's inequality evaluation demonstration with optics. What are the observables that have been done? So for polarization, spin states, are there various?
They are all photonic experiments. They're all using polarization.
Polarization. It's
But now the communication protocols, they will also time stepping. So you can have signals, even is non-orthogonal signals. Polarization is the easiest to describe, but that is not the only degree of freedom available. Even where you're sending photons, you can send two pulses slightly separated in time. And as long as they have some overlap, so they are not orthogonal. If they are orthogonal, then of course nothing will be run about the inequality, but you make them overlap a little bit. And then you can have a setting which is similar to this experiment, in the time resolution measure. Just like you measure this polarizer for direction, you have to have a corresponding degree of freedom. As a matter of fact, a lot of these communication protocols, they use the time stamping. They don't use the polarization degree. It has other kind of advantages for real time.
Regarding the statement which you wrote that correlation is not same as correlation, I have a doubt. Suppose I have two entangled particles separated by a space-like separation. So when an observer measures one particle, it ensures that in other observer will get the corresponding relation there. Right? So measurement here will force the particle there to collapse, and the other observer will get value, and we will see that these measurements will be correct. So, it's right to say that the measurement causes the